Okay, so while we're gathering again, I had my colleagues from AFRL pointed out I needed to add one reference to that list from Dan Paxton and Tom Camming, I'm pretty sure. A 2013, it was a NASA technical report, and they had a good analysis of the Heiser and Pratt work and pointed out some things they need to do differently in analysis. And they have different results then in terms of the total pressure gain efficiency. And I'd forgotten that paper until they mentioned it. It's actually a pretty good paper. I'm remembering it even after you said I should have included that one. I will say as I went through this list, I couldn't come out with a clear like, okay, here's the difference in gain that I get constant volume to constant pressure, because there's different ways people report it. And that's why I put on the top 1 to 3 points. You know, what this comes down to is the thermodynamics of how you describe these cycles. See, this thermal stuff. But I apologize I didn't include that one because it's an important paper showing the debate about how much gain can you actually get from a pressure gain cycle. So you'll want to pick that one up as well if you get through this. So thank you guys, I appreciate it. I promised we'd take a look at you know, what actually goes on in a detonation. So Professor Elaine Oran gave me a couple of movies from her work, and these are just instructive to help you see the process. You see if I can get this movie going here. And okay, so what you're looking at, the top image there is, you know, a plane where you have a combustion wave starting at one side. It's moving into the blue region, which is fresh mixture, and there's an obstacle, and I believe this is just hydrogen transitioning from detonation. You can see it's starting to move, and then the image sequence actually kind of continues on the bottom so you can see what's going on. Now, the colors are, you know, related to the temperature, and as the thing is proceeding, look right in front of the deflagration, and then in front of these obstacles, you'll see the temperature starting to go up as that wave is bumping into obstacles and moving forward. So it starts to accelerate because you've got this feedback between the temperature rise due to the gas motion. You can see it more clearly now. And the thing is starting to pick up speed, moving forward. It's still a deflagration, and then at a certain point you'll see a sudden transition to a set of conditions where you see that acoustic waves creating that sort of crosshatch structure. It'll appear, I think, coming right up here. Now you're starting to see a true detonation, right? Just boom, that thing's accelerating faster than the wave speed that is in front of it. And you can see momentarily it will transition back to a deflagration as it flies along that channel. All right, so the point of the thing is the process of deflagration to detonation, it's really stochastic, right? You'll see regions that revert back right there. You can see it's a deflagration because you have the high reaction zone behind the acoustic compression region. So I just thought this was a great visualization to allow you to see, well, here's what we mean when we say I'm going from a deflagration, accelerating up, and then, you know, achieving a true detonation. So thanks to Elaine Oran for sharing that. And if we have enough time and, you know, you're not completely burned out, I've got another one that I think is also really interesting. We'll save that for later. So let's get back to the topics here. The notes include some references there from Professor Oran, which are really good reading. The 2015 article gives you kind of an overview of, you know, understanding of how detonations occur. So some really good combustion fundamentals there. We're going to move on and talk about rotating detonation wave engines now in the next few minutes. This is one more variant of pressure gain. I mentioned earlier, you know, people have built pulse detonation engine tubes, put them in engines, but you have to light them every tube and you have a mechanical valve. Well, what can you do with, you know, a different approach to detonation where you might put the detonation in an annulus, right? So if you imagine an annular region, that donut that I've got shown there, let me get a pointer so I can make this clear. This region here is the entrance for air coming from the combustor mixed with fuel. And then you see the cold blue region right here, and then a structure, which is a detonation, which is traveling around that region, and it's consuming the fuel that's entering from here, and then providing products, you know, out into the turbo machinery downstream, or directly to propulsion. So if you unwrap this region and look at just one of these structures, here's what you see. Reactants coming up the bottom, a detonation wave moving to consume those things, and then this region, interface between the fuel and hot products, is actually deflagration burning, right? Remember when you had deflagration, detonation, transition, you have that interface where it's ramping up, so you're burning some fuel in a deflagration. It's not good for pressure gain, but it's part of the process. But here you have this detonation, and it is just moving to consume that mixture very rapidly. So in a fixed frame of reference, as you see that going by you, the gas is flying out of the back end of that thing and expanding, and it goes right around that structure and keeps going. So some of the advantage here is once you get it started, it keeps detonating, keeps moving around that environment. There's an oblique shock wave that has to sit in there to keep up with that high-speed flow. This is not a completely new concept. People have noted these things could be built since the 1950s, but there's recent studies we'll get into here in a minute show there's some new opportunities for the concept. So that's rotating detonation engine. The details of exactly how that detonation processes the fuel to, like an engine process, to convert it out into energy that you can use in the turbo machinery. It's pretty involved, but like I said, the easy way I think about it is you have this detonation wave flying through that region. The gas behind it is then expanding out at high velocity. So you have this high velocity gas which is expanding. It comes back around through this region, right? This wraps again on itself, and the oblique shock, interact with that flow and turns it back upward. And so that's how it creates the pressure gain through that sequence of processes. It's a fascinating process, the way that it processes the flow. And I'm going to show you a movie of it here, I think, on the next slide, so you get a physical insight into how this works. Let me change slides here. By the way, I didn't plan this in advance, but Rob Flevson, I said that right? Flevson? Rob is here today, all right? And so if I get all this wrong, he's going to help me get it corrected. But he did this animation for Fred Schauer and company at AFRL. So let's see if I can get it to play correctly, and you'll see how this works directly. So this is just showing you the geometry that you're looking at. That annulus, it comes together. So you see the way that the thing looks, the air moving from those blue arrows through those holes through a specific inlet geometry, and then the detonation, as I just described it, is shown there, moving into the fresh mixture in this direction, and the product's coming out this way, and it wraps in on itself. Now I think it, sorry, got to restart again. I think it starts itself at this point, right? There we go, yeah. Okay, so now you see the detonation circling around in that region, consuming the fuel that's flowing in, sending products out of the back end. So you get a sense of that, and I think the image will change now to actually show you an experiment that mimics what you're looking at from a simulation from a movie. So be patient here. I think it switches next. This is where I'm going to get impatient and hit start again. There we go. So now you're looking at the same thing in an optical geometry. Flow's coming in this way. You can see the detonations. That was a quartz combustor around the detonation. You can see the detonation wave moving around, the products coming out this end. And I think right about now you'll see some path lines that were imaged from particles. So you see them jetting backward, and then when that oblique shock comes back around, it straightens the flow right back out, so it goes out of the tail end of the device. All right, so you have that process I just described of, that detonation driving the flow in one direction, then the oblique shock coming and returning it back, so you get this nice, almost steady flow coming out of the back end. So thanks to my colleagues at AFRL for sharing that. It's just a great, great image. And I've got one more so you can see the external flow. This is the geometry that you just saw the images of, the real piece of hardware. This is a so-called aerospike nozzle with the flow coming out. You can see it's clearly supersonic flow at that point. You have some shock diamonds that are surrounding that geometry. If you look at the device where you don't have this center body and just look at the flow, this is probably, really the key interest. The flow coming out of the back end, just in a Schlieren image there, you don't see a lot of unsteady motion in the flow. And that's, really appealing, right? I got to couple this up to turbo machinery. I don't want a big unsteady flow going to the downstream area. So that's the key point, is you have this opportunity to have almost steady flow coming out of the back end of the device. It's not completely steady, but it's certainly better than a pulse detonation device where you have this sequential, very large velocity going out of the back end of the device. I'll just show two more and then we're going to switch topics. Whoops. So we're doing work on this at our lab along with our colleagues at AFRL. We're trying to focus on land-based power generation. So we have a version, and again, we were helped very much by the Air Force to come up with a geometry to use the flow coming in the bottom here and then going through that small area mixed with fuel, and then that annulus region is where the detonation actually occurs. So we'll take a look inside of the device here. This is a pressure vessel that sits in, and the camera viewing angle is shown. You'll look right up the tail end of that while it's operating. So again, this is, the view. You're looking camera angle straight through the donut here. We're looking up the tail end here, and just compared two different operating conditions. So you can see the chemiluminescent signal from the flame is that, detonation is spinning through that device. I can't remember the actual, frequency. But at two different operating conditions, you change the operating condition. Here you can see you've got a couple of different waves that are moving through that annulus. So this is a fundamental question, like what controls the wave direction or even the number of waves? Because look in the simulation that I just, this is just one condition that we did in a simulation. You actually have two waves circulating in that environment. So, that just is the way that it resolves the features of the flow. It has two waves that are operating in tandem in the detonation, and so as you change operating conditions, you can actually see changes in the number of waves, sometimes changes in their direction. So the physics of how that happens is something that we're studying along with many others right now to understand, well, what controls the wave directionality and the number of waves. So that's all we're going to say about pressure gain combustion. We've covered all the different technologies. Question? Yeah, there's a number of ways, but typically you have something that starts a detonation by just forcing flow into the device with a separate detonation device. So, it's actually easier to start than we thought when we got into the work. I mean, some of the geometries we can start it and it'll detonate just on its own due to the geometry. So. And
is there a possibility to flashback?
Well, there's lots of details of the inlet I can't get into today. Obviously, you want that stuff mixed so you can support the detonation. So if you don't do that carefully, it's like any premix combustor. You can always have a flashback issue, but that's really not a big consideration here. I mean, good question, good question. But here is a big question, all right? So I showed a whole bunch of different approaches to try to do pressure gain combustion. What are the combustion research issues associated with them, right? You're all researchers. We just hit on a couple of them here, like, well, what's the physics that controls the wave behavior for rotating detonation? What controls the deflagration to detonation if I was going to do PDE? If I'm going to do one of the other ones, like a piston operating inside of a gas turbine cycle, I've got a new set of combustion conditions. There's a lot of combustion issues there. We could probably get over those, but what do you think is the greatest challenge to develop this pressure gain for a power-producing combustor inside a gas turbine? So I'm not looking at rocket engines, not looking at direct propulsion, but what do you think is the biggest challenge to actually develop this thing and make it go forward as a technology? Supersonic turbo machinery? Yeah, if you don't expand it, then you would actually need to go that way. I think we're looking more at, well, how do I expand it down and then get it into more conventional? But great comment. Other ideas for what's the big challenge? Why can't I get there from here? Anybody? I was commenting yesterday to my colleague from Purdue here. I said, I bet you my answer will differ than everybody's in the room, because I have a way different answer than you're probably thinking about what's the biggest challenge. I really do. And I guess this just shows I've been thinking about programs for too long, maybe, huh? So you can put your notes there. Here's what I think is the challenge, all right? If you look at where I'm saying we would take this into a gas turbine engine, all right? We said before, these large combined cycles, they're almost like 60% efficient. They are 60% efficiency or more. They're way up here. They're 100 megawatts, huge machines, right? If I go down here into a small turbine, they have lousy efficiency, right? Turns out they have low pressure ratio and pressure gain. We were talking at the break. It's probably best suited low pressure ratio machines. That's where you get the biggest benefit. So you end up saying, well, that must be where I want to do it, but look what you're competing against. You know, it's not quite, but almost a constant volume combustion device, a piston engine. Those are already well developed. They have high efficiency right in that size class. So if I increase the efficiency here, I'm competing with a known technology. So what's the advantage? Well, these things have other kinds of maintenance issues you might get around if you had a non-mechanical pressure gain device, right? That might be a possibility, all right? If you look at simple cycle turbines, these things cover a pretty wide range today, from industrial machines all the way up to very large, you know, aeroderivatives. Their efficiency is certainly competitive with recip engines. That might be a good target. I'm not sure, all right? For the ones that are not aeroderivatives, they are low pressure ratio machines, and therefore they have probably a greater opportunity for benefit from pressure gain. But the challenge to me is, where do we put this technology on this map so it makes sense in a commercial world, right? I don't know the answer to that right now. We don't know enough about the technology. But at the end of the day, that's really the important question. The rest of the technical things I said are great technical questions, and it'll contribute a lot if you help us solve them to the broad knowledge. But to get it into a commercial world, we got to address that. That's the stuff I'm steadily thinking about. Where are we going to take this technology so that there's a pull for the technology? I think it probably is at the low end of this simple cycle machine, but we'll see. We'll see. It'd be great to put it in a combined cycle and get that. Remember when I started the talk, I said let's jump up above the line at 63. Problem is, I've got to do it then in a machine that already costs me, you know, what, 100, 200 million bucks. Means I got to find somebody who's willing to sign up for reconfiguring the core of that machine to take this technology. So it's a big investment. That's why I'm thinking about how can I do it in a small machine to get a realistic case that people are interested in, and let it gradually evolve into its application elsewhere. So something to think about as you pursue research. How is it going to get into its commercial use? It's really tough, and that'll affect, you know, the funding for the research, the interest in the research. So there's pressure gain, and I'm not going to summarize it right now because, believe it or not, even though it's 3:30, we got one more topic, and I'm a little bit nervous because it's the hardest one to explain, but I'll do my best for you here. But let's pull it up here. Talk about one more advanced technology. I can only find the right folder. Here we go. Okay. We are on the home stretch here. Just skip over those intro slides. A little bit of a recap. We were talking about Oxy-Fuel combustion yesterday. Big advantage if I want to capture carbon dioxide. It's easy to get the carbon dioxide out of that stream. But the problem was it costs energy to create pure oxygen, right? So after I go through making that pure oxygen, the way that you usually think about doing Oxy-Fuel combustion is you take that oxygen, since you don't want to melt all your hardware downstream, you dilute it again with CO2 or water. If a flame is a thermodynamic catastrophe, this is an engineering catastrophe, right? I put all that energy in to make pure oxygen just to dilute it again. It's not insignificant, right? It took you all that to get it. Once you dilute it, you took that availability back out again. Well, that doesn't seem like the right thing to do. It would be a lot better if I could just use that oxygen directly, you know, to burn a hydrocarbon and get energy out of it. That would be great if I could figure out how to do it, but the temperatures are just unbelievably high, right? So what am I going to do about that? Got to come up with something way different to achieve that. So this slide just recaps what I just told you. I want to make Oxy-Fuel an advantage because it takes a lot of energy to make oxygen. If I could find a way to produce power that benefits from the availability of pure oxygen, then the Oxy-Fuel approach would be an advantage. Well, this isn't, an unbelievable thought. There are processes where we take advantage of pure oxygen, right? I mean, people make steel and they like pure oxygen to get to high temperatures, or glass, rocket engines, pure oxygen is part of the propellant system. What do we do about a power system? That's the question that, we started looking at. So let's look at efficiency here in a little bit more detail. Sorry, I keep walking back and forth here. I got my pointer finally here. So efficiency, I'm plotting up here efficiency versus temperature. The blue line is the Carnot efficiency. These are technologies that we use today. Here's gas turbines, a simple cycle, a combined cycle, pretty high. Here's, a conventional steam boiler, and here's, a more advanced one. The point is we still have a long way to go to get to the Carnot efficiency on those. We're working on that. But right now we're limited in terms of the temperatures by materials that we currently use. If I do Oxy-Fuel combustion, I'm taking that temperature even further out in this direction. I don't have any technology right now to get the energy out from those temperatures. So we got to come up with a way to do that, and that's what this is all about. There we go. MHD, Magnetohydrodynamics, is a way you could do that on paper. All right? So if you've never heard of this before, I think most people had heard of it, yeah? Give me a show of hands, you've heard of it before, if yes, or so there's some that have, but not everybody, okay. So the idea is you take high temperatures possible with Oxy-Fuel and create an MHD topping cycle, and that's possible because you have pure oxygen, and then you take the exhaust of that system out to some kind of steam boiler. So how does this work? Well, you need to just recall how a conventional electric generator works, right? I mean, a generator that uses copper wire. You take a piece of copper and you push it through a magnetic field, and the magnetic field will push back as current flows through that wire, and that's how you make electricity with a conventional generator. You use a magnet and you push a conductor through the magnet. Well, MHD works the same way, but instead of pushing that copper wire, you take a conductive gas and you push that through a magnet, and just like a piece of copper wire flying down through that between the two anode and the cathode on this side, that moving gas, conductive gas, in an electric field will generate power as you push that gas down through the region. So if you take a source of hot, and I emphasize it's got to be electrically conductive gas, push it through a magnetic field, and then put electrodes on either side, you will get electric power out of this, and this is something that's been widely studied in years gone by. We wanted to look at it again for Oxy-Fuel applications. So if you did this as a combined cycle, you could reduce it to practice. It's got to be, with the technology that we have today, a combined cycle. Let me explain why. We'll talk later about most MHD concepts will only produce power above 2600 Kelvin. Now that is hot, right? But if you do Oxy-Fuel combustion, you might get 3400 Kelvin up in the combustion region. So if it's only going to extract power down to 2600 Kelvin, then you need to take the products from this MHD cycle out to some other bottoming cycle and get the rest of the energy out of that, convert the rest of that thermal energy. But you can still get pretty high efficiency, right? Because even if I'm only taking a small portion of that sensible energy, pressure energy, converting it out in this top part, the combined cycle efficiency, so let's say at the topping cycle, I just take 10% out, 10% efficiency of conversion. I can still add that to a bottoming cycle, which today might be around like 45% efficiency. And so the way you do that math to, in a combined cycle is shown here. So you might get a 50% efficient power cycle if you combine these. Now that's not the end of the story, because you could, in principle, increase your extraction of enthalpy out of this system more than what I've shown. But that's what I put there is actually a quote, reasonable expectation for what you might be able to do with technology that we know could be built. We don't know if it would last, but we know you could actually achieve something like that. So we'll talk about how that's actually done in the next few slides. If you're familiar with this technical area, you might know that back in the 70s, 80s, and ending like in the early 90s, MHD was actually a big topic of research for power production. It was viewed as an emergent technology for maybe increasing the efficiency of coal power production. In Russia, they had a very nice demonstration of this, and it's shown in that photograph. I think that was a 25 or 50 megawatt natural gas-fired MHD generator that operated, I think, outside of Moscow and put energy on the grid. And here in the United States, we developed the technology for coal, and it was a success technically. You can go back and read the reports. It never panned out economically, and the reason was the life of the electrodes at that very high temperature just too short. So you ended up, I got to spend too much money replacing electrodes, but and then the other thing was, ended up having to use a lot more seed material, which we'll get to in a few minutes here. But it can work technically. I mean, people built these things and operated them, and we have all that data actually within DOE. So why look at it again? And believe me, I've taken a bath a few times on this. I've pushed this idea forward. People are like, why don't you look at that again? That can't work. All right, so I've had to learn to be a little bit thick-skinned because I think we should look at this, right? It has some potential, and we need to do something truly innovative because the times have changed dramatically in terms of technology and the need. Back when we looked at this in what we call the legacy MHD program, no one was interested in managing carbon dioxide. It wasn't even a thought. Well, if I'm going to do oxy-fuel combustion today, all right, it is a somewhat natural driver for MHD because of those high temperatures, as I said. Probably ought to look at it, huh? At that time, there was a lot of money spent on MHD because the only way people could prove it out was to build a very large demonstration. Why? Because we didn't have reliable models for virtually anything at that time. We didn't have CFD at any significant level. We were still doing like cold flow CFD at the time, right? Well, today, if we had simulations that were validated, we could test a whole bunch of concepts on a computer. Probably seems like you ought to take a look at it in that way without spending a lot of money on very large demonstrations. At that time, no one was thinking about CO2 capture, so oxygen production wasn't really even much on the horizon. There were some people looking at it. But because of work on oxy-fuel combustion, the air separation units that we build today are substantially better, 40% less energy use than in 1990. So the energy I need to make that oxygen, significantly down. And here I'm proposing a technology that takes advantage of it, right? Gosh, I think we ought to look at this again. Back at the time when the original MHD program was being conducted, SOx and NOx, if you are my age, you remember, acid rain issues were really significant in our country because there was sulfur from uncontrolled sulfur emissions from coal plants. And so we were starting to address that. So people were talking about new technology. What am I going to do about sulfur control and NOx control from that new technology where the temperature's even higher than the existing technologies, right? It's going to be a big problem for NOx. So you read that earlier literature, a lot of issues what to do with it. Why? Because the exhaust was by design going to go to the atmosphere. If I'm saying from the get-go, no, I'm going to catch the exhaust from oxy-fuel for CO2 storage, I'm not venting any of this anymore. I don't have SOx and NOx control. Instead, it's the same capture gas processing unit that we developed for oxy-fuel. So that's off the plate. Not thinking about that anymore. At that time, to go out and buy yourself a magnet greater than 6 Tesla strength, big deal. I mean, people could build them, but they didn't have the materials that have been developed since then. There's advanced magnet technologies you could use to actually provide the magnets that you need to drive MHD. At that time, analog electronics. I mean, when that program started, there were still people doing controls with vacuum tubes, right? That's all changed. We now have advanced electronics, and I'll mention earlier, they probably would help you avoid issues of arcing that plagued the electrode life in these early designs. The legacy MHD program, because of the cost of demonstrating the technology, right, I could only pilot it, I couldn't use a model, they had to understandably focus on one generator design, a linear generator. We'll talk about that in a minute. Couldn't look at all the different options and test them all out. Well, we're saying if we can do correct models, then we can go through radial, linear, all kinds of geometries to see which one would actually work well. This last one, or next to last one here, is really interesting. At the time this program was conducted, you'll see the geometry of the channel for MHD power extraction. It's pretty complicated. I mean, you have like cooling flows, you have a lot of, electronics, electrical connections going in there, and that all had to be machined and put together, by conventional means. If you approach this today, I think you might be able to just manufacture with additive manufacturing, have a couple of segments that you build, put them together. So we have new approaches to build the thing. And then finally, and this is one I'm really keen on, right? I talked about the conductivity of the gas. Remember, the gas has got to be conductive to make this work. At that time, there was run route, and that is to put in an alkaline material as a seed material, which is conductive above about 2600 Kelvin. And that was the only way you could get to a conductive gas. It may be the only way today. We don't really know. We are looking at ways to inject cold plasmas into that system. That's why I came and sat with a lot of interest in Professor Ju's lecture, because we're very interested in non-equilibrium plasma, not just for this technology, but for a bunch of other ones. So this is really our aspirational goal. Can we use nanosecond pulse discharges to sustain non-equilibrium plasmas? And actually from here at Princeton, Professor Dick Miles has actually done that in an air-driven MHD channel, kind of a low-temperature small device. So we think there's some opportunity to basically rewrite what we thought from that earlier MHD program. So we'll see if we can do that. We're in the midst of this right now. There's a whole bunch of related technologies as we work through how do I do non-equilibrium plasma, how do I control the flow. I'm not going to go over this slide. It's essentially just a snapshot of all the things we heard from Professor Ju over the first 3 days of this week and in this part of the lecture. So even if we can't make the MHD process work, we expect to be able to spin off technologies in a number of different areas that are all plasma related. So this part of the talk dovetails with some of the things he taught us earlier in the week. So I said I was sort of like, oh boy, this is going to be the hardest part to explain. So maybe just sit back and relax. If the math gets a little bit cumbersome, let's just focus on the physics here, all right? So you'll know kind of, here's how this process works. So just a couple of little fundamentals here take us back to our undergraduate physics class. Electric field is a vector, volts per meter, so it points in some direction, and it can be described by a potential. I notice in your printed copy, for some reason the grad symbol doesn't print, so I've noted that here. So the electric field is a gradient of the voltage. If you just deal with one-dimensional problems, one-dimensional, the electric field is the voltage divided by a gap, all right? So that's how you define electric fields. By convention, the electric field points toward the low voltage region, and if you take a charge and throw it into an electric field, if it has a positive charge, it will get pushed along the lines of the electric field, and the expression for the force is the charge times the electric field. If it's negatively charged, of course, it goes the other way. Less familiar, the magnetic force on a charged particle. There you have this, if you have that particle moving with a velocity, uq, the force occurs at a right angle, the cross between the u and the b vector, the right angle product there. So I always have to hold my right hand out there, line it up, u, the direction I've got shown there, and then wrap that toward the b, and so my thumb is pointing down to where you see the fb pushing the particle down at a right angle. So if you write out the expression there, the force due to the magnetic field B is Q times U cross B, and then if you divide by the charge right over there, just like when I did that over here, I came up with an electric field. You might say, well, when I divide by the charge, force divided by charge, it's almost behaving like another contribution to the electric field. And if you study that sort of thing, you realize it is a manifestation in a similar way. That's how magnetic fields work. They're manifestations of relativistic effect between moving charges. So anyway, so I'm going to, in this talk, define the net field that a particle sees as the true electric field, and then U cross B. So that's just nomenclature I'll use to make it convenient. The particle responds to both the electric field, and if it's moving, the presence of a magnetic field at a right angle puts the force on it. So that's how charges interact and operate in a magnetic field. So we can use that to generate electricity, as I've got shown here. And I apologize, I found the typo there. Luckily I did find it. So if you're taking notes there, you need to correct the K should have been a J here and a J right there. But here's how it works. I have conductive gas flowing through this channel with a height B. So it's coming down this way. The U cross B creates the force on the charge that's flowing down that channel. Right there, U cross B in that direction, the negative K direction. And so that is what drives current through this external circuit. So is that clear how that works? It's actually pretty straightforward. And again, the way to think about it, if you had a copper wire that you were pushing down the channel and the wire was connected between the top and the bottom, so maybe it's easier to think of it as a rod that I'm pushing down there, all right? It's just like a conventional generator, just moving through that magnetic field, and it's generating current as it moves down. So that's how it's similar to a conventional generator, right? Instead of a wire pushing down, like a rod going down there, I'm just moving the gas down the same channel. So how much current actually flows? So lots of math there, but I think you'll easily see the bottom line result down here. I'm showing the channel again with the fluid flowing down this way, and then the external circuit running around here. So the current that flows is the conductivity of the media times that net field, where the net is both the electric and that magnetically induced electric field from the flow down through the magnetic field. As I've drawn it here, the magnetic field is coming out of the page, right? So that's, you don't see it on the diagram, but it's responsible for the electric field that's generating the current flowing around that device. So the current density is the conductivity times the net field. That net field is expanded out here. The imposed electric field from the external circuit plus that U cross B product. So if I'm looking at just a one-dimensional problem, I can take away the vector notation. That's E0, which comes from out here, minus UB, which is generated inside the channel. So let's just quickly go through this. Again, when you get down to the bottom, it'll be very clear, even if you're not following the exact step-by-step here. The E0, the gradient of voltage from the external circuit, is just the low minus the high, the negative of the gradient. All right, so the gradient itself is low minus high divided by the distance. So that gives you the imposed field around here. The E0, I've expressed it here. And that equals the current that's flowing around the loop times the resistance. That's that voltage drop, right? IR is the voltage drop here, divided by B to give you the field across that region, which is that vector, E0, right there. The generation is UB pointing in the other direction, all right, just from that right-hand rule. So I might be, you know, the first time you see it, it's like, whoa, there's a lot going on there. You said it quick, but it's not real mysterious, right? This is the electric field generated, like pushing that conductor down with a velocity U. This is the field that you impose because you have current flowing across a load resistance on the outside. And very important, there is a resistance to flow, current flow, inside of the channel, which I'm showing here as RI, or internal resistance. So if you just follow that development through, the current that's flowing is what's the generated voltage, UB, that's what comes from the flow of conductive media in the magnetic field, divided by the resistance inside of the channel plus the resistance of the load. So I hope you're like physically seeing it, even if you didn't quite get every step of how we got there through the math. So if you actually take that thing out and make it open circuit, this is just the open circuit voltage, all right? So the open circuit voltage divided by the resistance, the internal resistance and the load resistance. So just one more look at it so it gets a little bit clearer and maybe easier, all right? If I do the same problem again and I don't have any load, it's open circuit, all right? And in that case, the current that's flowing is 0 because it's an open circuit. So if I just go back to my expression for current density, the E0 minus UB must be 0. And so on these two vectors, the applied voltage has to balance the generated voltage. So nothing flows, right? And I show that with those two arrows. And then as I start to generate, right, what I'm end up doing is I'm actually reducing the applied voltage a little bit, and so I'm actually flowing current because this is what's generating the current flow, the UB product from here. And then finally, if I just short the thing out, well, in that case, there's no applied voltage because it's shorted, right? And so the current flow is just regulated by the internal resistance flowing across that channel in that gas phase, right? So those are the three kind of limiting cases of what you see when you actually connect this up as a generator. So here I show it as more of an electrical. I'm sorry I'm looking at my watch because I couldn't remember when we quit. There's another break coming here shortly. I'm showing it again here as an electrical analogy where this is what's going on inside of the gaseous media. The open circuit voltage is generated by the UB product right there, and that causes current to flow. It's resisted by the load that's attached externally and then what happens internally. So if you define this quantity K, it will appear several times throughout the rest of the talk today as the load voltage, the voltage drop across the load to the open circuit voltage, what I would get if I disconnected that. That K can be expressed several ways. The load voltage is the current flow times the load resistance, and then the open circuit voltage is I times both of those. And so there's several different interpretations for K. It's the ratio of these two voltages. It's the ratio of the load resistance to the total resistance that's shown here. It's also an efficiency because if I multiply this term by I over I, that becomes the power that's generated and the power that is actually going to the load. And it's also the ratio of the applied field to the generated field. The reason I'm going through all these different interpretations is people use them in different ways, but the main thing for today's talk is K is just a loading parameter. It tells you how much load relative to how much could I actually generate. And typically you'd run a system at a K factor of about a half because that's where the power density is greatest. So it's really the only point of this slide is to help you understand there's a parameter that tells you how much am I loading it. All right? And you want to run it at about a half because that gives you the greatest power density. At a half, this internal resistance equals the load resistance. And so that's how it gives you, it's like impedance matching in any power generating device. And that's actually on this slide. Sorry, I should have switched here. So if you take the definitions of K and you work through the electrical terms of the current flow is area times the current density, and then put in the expression we had sigma times the conductivity times the voltage times the electric field, that gives you UB times the loading factor, K minus 1. You just substitute in here. So there's some algebra you can work through. I mean, it's hard, at least it's hard for me to grasp the algebra when somebody just presents it quickly. But the point is, when you work down through that algebra, the power density, okay, comes out as the square of the velocity and the magnetic field times this loading parameter, K minus 1. So the message, the take-home message here, if I want high power density, that term is maximal at K equals a half. That's why I said you want to load it up to about a loading factor of about a half. Remember I said it was an efficiency, and you might think, well, that doesn't sound right. We'll get to that. You got to build the thing around power density because you spend all the money on the channel, you want to get a lot of power out of it, right? So you run that at a half. Also very important, to good power density, you need to have high velocity in the flow. all right, because it goes as a square. So higher velocity is really nice for high power density, and it goes as a square of the magnetic field. So you want a strong magnetic field. I think that's understandable. And very important for later, the power density is proportional to the conductivity in the media. So if I'm going to go through and I have a great idea for MHD, I'm going to build one and design one, and then somebody says, well, how much power is it going to produce? Because I got to spend all this money to get to that power level to build this thing. If I have a mistake in my gas conductivity, it's directly related to how much power is going to come out of that device. So you better know that number pretty accurately, is my point here, all right? So high velocity helps, high magnetic field, know your conductivity, run it at a loading factor of 1/2. That's the main points, aside from working through the development. Take a breather, right? So we just said, here's a simple model for MHD power generation. I'm just going to, like a wire, push that through this magnetic field, and I'm going to generate. Now, how did that happen? I'm sorry. I'm going back here. There we go, right here. So I just explained to you in that simple case that the current that flows in that gaseous media is just the conductivity of the media times this voltage, times that electric field, which is the imposed electric field from the external circuit, minus what you generate. Now, mind you, it can be a negative term, so it's like plus what you generate by pushing that gas through the conductive media. That's what I told you. And we did a few more little, like, here's some parameters that you need to know about power density. Well, it's never that easy, all right? There's a complication that arises from the Hall effect. Anybody remember the Hall effect from your days of studying physics and that sort of thing? It's this. Once the current starts flowing, right? Remember, it's not really a wire, right? The current can go wherever it wants. So if it starts to flow in this direction, it's not just the velocity of the electrons going with the gas. You're getting them to flow this way. Now that motion interacts with the magnetic field at a right angle, and so it starts pushing the electrons in a different direction. And even if you don't follow the math here today, you can if you just go through the steps I'll show you here. The message is it tilts the field that would otherwise go from top to bottom. And that creates some difficulties for extracting the power. So rather than go through the math in detail and then like, oh, what was that all about? I'm just going to jump right to the conclusion, then I'll show you the steps we got there, okay? So here's what we've got. This is the current density in an actual system accounting for that Hall interaction. And now I have electric fields. Remember I said it tilts the field not just in the Y direction going up and down, but there's another field to be concerned about going along the channel, all right, the X direction. So I said it tilts the field. You've got now electric field in X and Y directions. And there's going to be a current that flows not just in the Y direction, but also in the X direction. All right, and the expressions I've got there are general, and depending on how you arrange the thing, you'll see we'll specialize them to different geometries of electrodes. So in fact, you can cancel out the Hall effect. All right, so that's the main message I'm going to leave you with. Even if the math gets like cumbersome, you know, oh, we're just trying to get to the point to show that Hall effect of tipping the field, I can counteract it with good engineering. So we'll take a look at that, and like I said, hopefully I'll do a good job explaining it because it does get a little bit complex as we move through this. So complications from the Hall effect. This is stating again what I just said with some graphics here. In most MHD charges carried by the electrons moving in the flow, the electrons move against the electric field. The electric current has an associated charge velocity, obviously. So rather than speaking of electric current, I'm going to speak of the velocity of the electron, U sub E, and now that is interacting with the magnetic field, that is the Hall effect. So let's look at the vectors, how that works. Here's the gas flowing through the channel, velocity U, and then as I start to flow current through the system, it starts going up this way, but now I have to account for the fact that I have UE, the velocity of the individual electron, cross product with the the magnetic field vector B. So this is actually the UE cross B, and this is the U cross B. So this is the force the electrons are feeling from the moving fluid, and this is the force they feel from the Hall effect that they're now flowing through that system in a different direction than the fluid, right? Did that make sense? I mean, that's really the physics of it, right? I'm pushing them through in one velocity this way, and then as soon as current starts to flow, they're moving that way. So now I have that combined vector that's interacting with my magnetic field coming in. I don't have a third arm to point in this direction, but you see what I'm saying, right? So you have to account for those collective velocities to get the net field. And again, the point is that Hall effect tilts the field from just going up and down backward. And how much does it do that? Well, that's where you have to do a little bit of math. And if you want to, if you're really interested in this, you can just take this page and look through the definitions that we've got here, the velocity of the electrons when current is flowing is given by the mobility times the net field, which is expressed here. This is the Hall effect over here. Mobility is related to conductivity, just as I've shown here. You assume, and this is a good assumption, the magnetic field is unaffected by the flow of the current. That is a good assumption in this particular class of problems. It's not so good if you're trying to calculate astrophysical problems and other things. But if you make that assumption, and then you express the electron velocity in its two components, the current density in its two components, and just plug that into the equation above, do some math. It actually is straightforward. It's about a page and a half algebra. You will come out to expressions for the current flowing in the x direction, the current flowing in the y direction, the net electric field along x, and the net electric field along y. So you can go through and actually take the steps, and you'll come to that conclusion. It really isn't very hard. It's just a lot of work. So let's take a look at what it means. If I take those expressions that I showed for current and voltage, and I look at what's called a simple Faraday generator, I put a conductive channel here and here. The fluid is now flowing along the channel in that direction. The electric field in the x direction has to be 0, right? Why is that? Do you see why? I put this conductor on top and bottom of the channel. Well, I can't have an electric field there. As soon as I get an electric field, current will flow to cancel it, right? That's what that conductor does. So there's no x direction, so I just plug that back into the expressions I gave you, and you'll find out that the y-directed current flow is this expression. Now, if you flip back in your notes and compare that, I'm doing it for you right here. In the simple generator analysis, where I wasn't paying attention to this Hall effect, this was the result for the y-direction current flow. How much current is flowing between these two channels? Well, if I compare this to this, where I'm accounting for the Hall effect, the only difference is this factor. 1 over 1 plus mobility squared, magnetic field squared. Turns out this is a number between like 1 and 10 for most MHD. Well, that's not so good. I'm trying to get power out of these two things. This is the thing that's driving that power, and I just said this Hall effect is decreasing it by about a factor of 1 over 10. It's not so great. And then the other thing is, I talked about this, you can solve the same set of equations for the current that's flowing along this direction, all right? And that has an expression that's shown right here. And it turns out there's that same product, UB, I said it's like, could be a number like 10. So you could actually have more current flowing back and forth, doing nothing for you, right, than going out of the top where you're trying to pull the power out. So that doesn't sound like a very good prospect. It all depends on how big this quantity, UE, mobility, times magnetic field is. And you can calculate that. I show on this slide an analysis to show you what it means physically. It actually has a name. It appears so often, that combination of mu EB. It's called the Hall parameter. And because it's late on Friday, rather than going through what is actually not very complex math, you just balance out an electron in a magnetic field, If it's moving, it always has a force at a right angle, so it spins at a frequency, a cyclotron frequency, and it also, because it's sitting in a gas, will be bumping in to other species in the gas phase, and so you'll have some time between collisions, mean free path. So it turns out mobility here is equal, after you go through this, the product of that cyclotron frequency and that time between collisions. So if that product, this Hall parameter, is very large, what it's telling you is there's a lot of spinning around of that electron before it bumps into somebody. If it's a small number, there's lots of collisions before it gets through one cycle. If it's a number, order of magnitude 1, it's bumping into something about every time it goes around. So it just gives you a physical sense of what this Hall parameter means physically to the individual electron. What does it mean in terms of the performance of the Faraday generator? Well, remember I just said that mu EB, it's the Hall parameter, omega tau. This is the same expression you saw on the previous page. So this quantity is like between 1 and 10 for MHD. So again, the point is you really cut down the current that's flowing through the device with any reasonable value of the Hall parameter. Don't want it to happen. Same thing here, right? I said, if this is 10, the current that's flowing along this direction might be 10 times what's flowing in the direction that you want. So we got to figure out what to do about that. How do you improve this? Luckily, very smart engineers from a long time ago realized I can get around it. Here's how. Segment the electrodes on the channel. So what I'm showing you is my, again, bad graphics skill, but you get the point. Instead of a single conductor at the top of the channel, I just break it up into discrete points along the channel, and then I use each one of those to drive its own separate load. See, the load's supposed to be shown here. There's a wire snuck around the back. The top and the bottom are connected. Well, that breaks up the current that would flow down the channel in this direction, right? How come? How come it breaks the current up? Why is there no current able to flow up and down the channel? This isn't a trick question, but in fact the answer is down at the bottom. But anyway, how come it breaks it up? It has nowhere to go, right? I mean, if I have currents trying to flow this way, where's it going to collect? Now, you can get a very large voltage gradient along that direction, right? But you can't flow the current. So if you go back in and use the expressions I gave earlier and you actually set the current along x to 0, you can solve for the current, the x direction current is 0. That helps you then define the net electric field on x and along the y direction, and then plug that back into the current that's going in the j direction. And once you do that, you'll have an expression for the y direction current up and down on one of those individual channels. And lo and behold, if you follow through and cancel out terms, you find out the y-directed current is just the conductivity times the net y-directed field, which is the exact same expression we had when we looked at a simple generator. That's pretty clever, right? We started off with this simple idea of like I'm going to treat it almost like a wire moving through that, and we bump into, oh no, it's a conductive media. If the current can go wherever it wants, the field tips over from the Hall effect. But we said, all right, let's break the electrodes up so the current can't flow that way. And you end up with a final solution that goes right back to the original value like you didn't have any Hall effect. So that's a pretty good finding, pretty good way to do it. But there's a practical disadvantage to doing it this way. What is it? Hint. Count the number of wires, right? For every electrode, I have to put its own load. And they were trying to do this in 1975, 1980. You start thinking about controlling all those discrete circuits, it's just not going to happen. So people didn't want to really do discrete loads. They wanted one wire out to the load, maybe two. So people thought harder about it. Maybe there's a better, simpler way to make this work. Maybe I can still get the advantages I want. Let's look at a different electrode geometry. So here you have the individual electrodes shorted out, all right? Well, that just doesn't sound right to me. I'm going to short them out, right? Sometimes you say short, you don't want to do that. But the way this thing actually works, go back in and substitute in the short here, so there's no Y-directed electric field because you're holding it at the same potential, right? Stick it back into those equations and solve for the currents and the voltages as before, and what you'll find is the open circuit voltage in this direction is actually quite large. Remember I said omega tau is like numbers like 1 to 10? So now I multiply that times UB, it actually gives you a pretty big voltage, and all you need to do is connect your load up to the front and the back of the generator. So now I'm down to one wire. And this thing is just a piece of metal which I got current flowing in, and the reason it's called the Hall generator, that current that's flowing around that short circuit is actually what you're using as your flow to set up the electric field. This is interesting because, I gave you the example, we're pushing the fluid down the media, like a copper wire. Here, you're using the current flow that you get from the short as the push. So it's an interesting way to take advantage of it, and it actually gives you, some good power output. So this is what's called a Hall generator, and, again, the advantage here is you just have one wire and one load. Now, there's very clever people that said, that's an interesting idea, but I don't like having all these electrodes shorted out. So can I come up with a different way to get the same effect? And I just think this is so ingenious, right? Some engineer, really credited with some great creativity here. I hope you can catch the geometry. If you imagine a flow coming down a pipe and then expanding into an annular region, right? So is that clear what you're looking at here? The flow is coming in here. It stagnates right at the bottom. So I'm showing the cutaway view of this geometry. Stagnates at the bottom, then starts heading out in this direction. What I then do is put an electrode here, an electrode here. I have my current flowing, I have my fluid flowing out in this direction. I arrange the magnetic field in this way, and now the short circuit that I generated here and here, that short circuit is actually inside the gas running in that annulus. So you're trying to set up a current in that annulus because of the magnetic field, right? You have this magnetic field going this way, you have the flow moving this way, U cross B tells you it's going to push at a right angle, and so the current actually runs, the Hall current runs through that perimeter. All right, so that's how you set up the Hall current, and you pick up the voltage generated just like you did here by connecting to the front and the back of that expansion. I thought that's really ingenious, right? These have actually been built and tested, I think, a couple of cases in Japan. They look like they have some advantages. There's some tremendous fluid mechanics problems here. If you want to do really complex fluid mechanics, this is probably one you'll want to take a look at. So, but it has huge advantages in terms of how many wires you need. You don't need a lot of electrodes. There's only 2 of them in the way I've shown it here. You could put more in if you wanted, but you only need 2 of them. And then finally, the one that was actually embodied in tests for the US program in MHD a number of years ago, an intermediate between that Hall approach where you just short the things out, generate the voltage drop in the axial direction. This intermediate approach is kind of an interesting thought, again, very creative. You connect up the electrodes to deliberately force an electric field to slant against what is imposed by the Hall effect. Remember how I said the Hall effect tips the field? Well, if you're clever, you can just hook the electrodes up to apply an imposed electric field that actually matches the slant of the Hall effect. You're just tipping it. And if you run through the math there, you'll find pretty much the same thing. You can cancel out the Hall effect for at least one condition, right? It can't be all conditions because the change of the tilt is governed by how quickly you're moving that fluid down the channel, because that's what sets up one of the fields. But it's a very clever idea, and like I said, it was embodied. This is an MHD channel from the from the US program. I don't know if you can make out internally. You can see the actual electrodes slanted. You can probably see it even clearer in the way some of the wiring is in the outside. By the way, look at the complexity of the mounting all those electrodes. That's why I said current development, you would actually be able to manufacture this probably a little bit easier than stacking a bunch of plates together. So very interesting idea about how you would actually control the Hall effect. I think, is it time for a break? It probably is. You're all looking like you're drinking out a fire hose here. Some of this gets pretty dusty. Let's take a break until 4:30, and then we'll come back and wrap it all up.